Hello, everyone. Thanks for coming to my talk. Today, we're going to talk about TableGen Backend. So just a little bit of myself. You can call me Min, and I'm currently a fourth-year PhD student in UC Irvine. I'm also the maintainer of M68K Backend, and I actually published a book earlier this year, which I will briefly mention at the end of this talk. So today, we're going to talk about TableGen Backend. But first, let's introduce TableGen. So TableGen is a domain-specific language originally from the LLVM project. And in case you wonder, is Turing complete. And it was originally designed to describe instruction info for LLVM backends, like the operands for instruction, the assembly syntax, and some instruction selection rules. But nowadays, it's used in wider varieties of domain inside LLVM. For instance, it not just describes the instruction selection rules, but also the scheduling infos. And it is also used to declare metadata. And my personal favorite is using in the option subsistence, which is used by the client compiler flag system. So the client doesn't use the LLVM command line, but use this to model the driver and front-end options. So let's look at a simple TableGen code example. So a class inside a TableGen is used to describe an layout of a template. So in this template, we'll use so-called fields to describe the prospective properties. And now we will use the def syntax to declare records. So in this case, this records is created from the template stuff we see previously. So this record is just like encapsulations of data. And since it conforms to the template stuff, we will assign the fields accordingly to the template stuff. And of course, we can create as many records as we want. More often, we'll use the following syntax to simplify the code we wrote in the previous page. The variables surrounded by the angle bracket can be used to substitute fields in the class, such that we can have more concise code when we're creating records. And you might find, this concept of class and records in TableGen resemble to the familiar object-oriented programming languages. And indeed, both of them provide a way to encapsulate aggregate type data. But different from OOP language, the records are immutable, and the values in each field can only be constant values. It cannot be dynamic, like in this case. And finally, we can only create a constant number of records. Another concept that might ring a bell in your brain is relational database or even spreadsheets. For example, we can rewrite our previous example into the table like this, where each field is a table column. So first, fields are similar to columns, but different from a relational database. Records do not belong to any tables. And although we introduced TableGen class as a template, but actually this kind of strong structures are not required. So you can definitely create records like this, that records did not created from a specific template or specific TableGen class. And my personal favorite is that you can even create records without any fields, like showing in the last examples. And when it comes to data types in TableGen, most of them are pretty straightforward, like integers, string, boolean, and bits. We can also have bit vectors, list with arbitrary data types, and a special data type called DAG, which stands for direct acyclic graph. So this kind of data type is used to represent any data that can represent in direct acyclic graph, like an expression trees. And we will have more cover on example of using DAG, but here we just introduce the syntax. So you will actually have a really list the programming language styles, where you have a bracket, and the first one we call it operators, followed by a comma separate list of arguments. So now we learned the basics of  but how can we use these TableGen records? For instance, the example records we shown earlier are kind of like merchandise. So we can actually convert these records into, let's say you're running a warehouse and you can convert this into electronic records for this warehouse. You can also convert these records into the e-commerce website HTML code you're running, or similar to the e-commerce website, you're converting them to the physical, like shopping catalogs, magazines. So the thing or the tools that do this conversion is called TableGen Backend. And more specifically, each TableGen backend is going to take the result generated by the TableGen parser, also provided by the LLVM libraries, and convert them to arbitrary type of outputs. Let's look at a real-world example before diving in. The LLVM TableGen program is the TableGen driver in LLVM. It contains many TableGen backends, like the insert info and deck ICEL backends listed here. Given an info TableGen file, each of the TableGen backend can generate different output files. In this case, the output files are just normal C and C++ code. So this is how TableGen backend and TableGen tool looks like in real world. So let's look at the topic we're going to introduce today, TableGen backend development. So first, why should I learn to write a TableGen backend? So TableGen, despite being a DSL, a domain-specific language, is actually really versatile. It can basically do anything, and it's pretty generic. But to do these tasks, it always requires a specific TableGen backend. Fortunately, LLVM has provided nice infrastructure to work with the TableGen code. So you don't need to parse the TableGen code yourself if you're writing a TableGen backend. So so in the rest of the talk, we're going to motivate our discussion using example projects. And the topic of this example project is, recall in the previous slides, we've shown that TableGen is a more flexible way to represent static structural data. So compared to relation database, it's more flexible. So in this project, we're going to convert one of the most famous relational database scheme, SQL, and convert the TableGen code into a SQL code. So we have a TableGen code as an input. Then our tools, our standalone tools, SQLGens, as well as our custom TableGen backend, will convert this TableGen code into SQL code. So the first SQL syntax we're going to generating or converting is create tables. So create tables will create a SQL tables which represent the layouts of just a table, so that each row in this table can follow. And as you can see here, each field or each column has its own data types. And there's a special construction called primary keys. So primary keys is an identifier a unique identifier for each rows. So in here, we're going to use a primary key statement to designate the ID column as our primary keys for this table, customer. To model the statement, first, we have a TableGen class table, whose subclasses will be translated into individual create table statement. And each field in this class will become a SQL column. And to designate a field as the primary key, a TableGen field as a primary key, in this case, the ID field, we're assigning the primary key field from the table class to it. So we're kind of using the primary key field as a token to tell the TableGen backend we're going to write later to tell it that, hey, ID field is the primary key. Now we have the SQL table. It's time to insert some rows. So to insert some rows, we're going to use an insert into statement, which we provided the columns we're going to insert it and the values. This SQL statement is modeled by TableGen record creations. So recall the customer class we've been showing in previous pages. When we create a record using this class, the insert into statement on the right-hand side will be generated. So those two are the primary tasks we're going to do later. Let's look at the SQLGen tools right now. And recall that this is a standalone tool, so everything starts from the main function. And we're going to take in a shortcut here by leveraging one of the helper functions provided by the TableGen libraries, the TableGen main functions. So this function will do all the heavy lifting, including parsing the TableGen code and generating it as the in-memory representations, and passing it to the callback function. So the first argument of this callback function is the raw string you're going to output your results. The second one, the record keepers, is an in-memory representation of the parsed TableGen code. So you can see this callback function as the entry point to a TableGen backend. So let's see how to do the first task, creating SQL tables. Recall our goal here is to generate SQL statement on the right-hand side from our TableGen syntax on the left-hand side. Since we're generating create tables from TableGen classes, the first thing to do is enumerating all the classes. The get classes functions from the record keeper will return a map from the name of the TableGen class to a pointer to records. This record, the LLVM record class, is an important construction in the TableGen ecosystem. Despite its name, it's actually used to represent both a single TableGen record and a single TableGen class. This might sound a little bit weird at first glance, but you can think of TableGen class. Recall previously, each field inside a TableGen records has a value, has a constant value, and you can think of TableGen class being a special case where only part of the fields have values. And finally, to distinguish whether an LLVM record object is a TableGen records or class, you can use this isClass function to distinguish them. So now we learned that conceptually, TableGen class and records are just siblings. We can expand a TableGen record into a canonical form like this. Another thing you might notice here is that it's different from its TableGen record counterparts. The ID fields inside the customer class was not resolved to the value of primary key, which is 0. Instead, the ID field in customer class used the primary key variable as its values. That is because for a TableGen class, the TableGen framework doesn't aggressively resolve the values. So here, if we're asking the TableGen framework what is the value of the ID field for this customer TableGen class, it will actually tell you it's a variable primary key instead of an integer 0. And we will actually leverage in these properties later. And both of them are represented by LLVM records, as mentioned before. On the other hand, each field is represented by the LLVM record val class. So let's go back to the code. Now, for each TableGen class, we have its name and the corresponding record objects. First, we only care about TableGen classes that are derived from the table class. Then we can print out the first part of the create table statement using the class name. Then we enumerated the enclosing fields. And for each record val object, we can print out its name and get its data type. For integer, we're just using the SQL's integer type. And if it's a string, we're using SQL's var 255 type. In previous slide, we extract the name of the end type for each TableGen field, modeled by record val objects. One thing we haven't covered is the value of each field, which is modeled by an init class. Different data types of fields values are represented by different derived class of init. In addition to integer, string, and DAC values, there is a special one called var init. Remember, in a TableGen class, the value in a field is not aggressively resolved. So like in this case, the ID field uses the primary key variable as its value rather than integer 0. And this primary key variable is represented by var init. And this is how we handle the primary key resolutions. First, we're checking the value of individual field. If the value of this field is a var init and it's called primary key, then that field is designated as a primary key in this SQL table. So that's how we do the table creation. Now let's look at the row insertions. Our task is to generate the SQL code on the right-hand side from the left-hand side TableGen code. To retrieve all the records created from TableGen classes that are derived from the table class, instead of enumerating all the records, we can actually use a pretty handy function called getAllDerived definitions. And again, these are in-memory C++ classes used to model a record. So for each record object, we are again visiting its enclosing fields, represented by the record val class. First, we're printing out the field name. Then we're visiting all the fields again, but this time we're printing all the associated values, the init object. So these are the primary tasks we're going to do in this project. And in addition to creating SQL tables and inserting rows, making queries is also a pretty common thing for a SQL database. The syntax to make a query in SQL is called select from. On the TableGen side, we're using a class query to model it. The things go right after the select statement or directive are columns, the SQL columns you want to print. And this information will be stored as a DAG object in our query TableGen class. Then we're specifying the table we want to query from. Finally, we can add a conditional condition to filter out result using the where clause. This information is also stored as a DAG in our query TableGen class. One thing you might notice is that we don't actually have a name. So this is how we use the query class to create a record to represent the real query instance. But one thing you might notice is that we don't actually have a name for these records. And this is actually allowed in TableGen. It's called anonymous record. Another thing we want to focus on is the where clause DAG expression. What we're trying to do here is expressing the where clause condition as an expression tree. Let's take a look of how to write an expression tree using TableGen's DAG construction. In here, we want to model a simple math expression. And we have two TableGen records, plus and minus, that we're going to use later. First, we're tackling the arithmetic addition part by using plus as the DAG operator and the integer 9 as its first argument. And the second argument is actually another DAG. Note that in this DAG, we're actually using a string, mul, as the DAG operator to represent the multiplications. And finally is the arithmetic minus. So the bottom line is that both operator and argument in a DAG object can be any data type. It can be a record, it can be a string, it can be an integer. And the DAG is used to represent some expressions symbolically. So let's go back to our query example. So here we have more example of how do you express the where clause using the DAG. So for instance, this shows how can we express the amount greater than 8, where the GT operators means greater than. And also we have much more complex where clause expression, combining using the logical and some sub expression also as a DAG expression. There's one more syntax we added in our where clause DAG. The column followed by a $sign and a string called str. This is called a DAG, or sometimes called a DAG argument name. It has actually no effects other than a token used by the TableGen backend. In this case, for instance, we're using it to distinguish between column name and a literal string. meaning that only the DAG argument with this tag str will be printed with double quotes. Now let's convert all the query records. Here we're using the get all derived definition function again. For each query record, instead of enumerating all of its fields, there are some functions that help you to get the value of a specific field as a certain data type, like get value as string shown here. Then we're doing a similar trick to get all the SQL columns to be selected. More specifically, the get args functions in the DAG init will give you all the DAG arguments. Finally, we're handling the where clause separately. The term function arguments, the term function argument to visit where clause is the where clause to be converted. First, we're using the get arg to get all the DAG arguments. And if this DAG argument is another DAG, then we're going to recursively visit this DAG. Otherwise, we're retrieving the tag of this DAG arguments. If it is str, the tag is str, then we print it out with double quotes. Otherwise, we just print it as it. Finally, we're printing the operator between two DAG arguments. So this basically wraps up our projects. And again, what I'm trying to emphasize here about this project or TableGen backend in general is that TableGen is actually really generic. It can do anything. So it's highly encouraged you to write a TableGen backend and use LLVM as a library instead of just modifying the entry LLVM code and for your own custom task. And of course, in this tutorial, I only cover some common TableGen syntax. And there are a lot of other useful TableGen syntax, like multi-class is a really useful helpers for you to create multiple TableGen records at once. And there are also TableGen operators that it's like const expert in C++14 that's statically or evaluating the value in the TableGen parsing time. And there's also a handy string concatenations the palm sign. So all this sample code is put in this repository, which I will put in public later. Just be aware that actually I was planning to add more features in this talk, but eventually I just removed them from the slides. So actually in this code, it contains how we can insert hierarchical records via the foreign key SQL statement. And also some advanced feature that implement order by. And last bit is I use LLVM lists for testing, so it will be a good reference if you want to use LLVM lists on an out-of-tree project. And that's it. Thank you all. And I'm going to shameless plug my book here because there is a promotion this week. So if you use this promotion code on this website, you can get 25% off. And with that said, I am happy to take questions.
Thank you for your presentation, Min. Our first question is, can you please also talk about patterns and how to map assembly instructions using patterns?
Oh yeah, so I guess you're talking about the use case of let me fast forward to the DAG part first. This is definitely not assembly, but just put it here.
Sure.
So yeah, so in the backend, they actually use the DAG to model the input and output operands of an instructions. Then it will actually use a tag on each operands. Let's say tag DST represent the destination register of this instruction. Then it will put this $BST inside the assembly text, assembly syntax of this instruction and put it inside of it. Then finally the ASM printer will identify this, or it will generate the code for ASM printer to substitute this $BST with the real register allocated by the CodeGen framework. So that is, I think that is your question, like how the CodeGen framework try to incorporate the DAG and the assemblies, assembly code templates.
Okay. And on that note, with regard to the tags, are these only available for the DAG expressions? And if so, why are they necessary for the DAG instructions?
Oh, yes, this is only available for a DAG, and it can only be, it can be tagged on the operator and arguments. I don't know the real, I think it's just a historical reason where people only use the tag on the DAG. So yeah, so that's the reason it is only available for DAG.
Is it just one of the systems that has more need for that level of differentiation?
Correct. Well,
okay.
by far, this is the only place we need this kind of distinguish.
Okay. Earlier on in the presentation, you also mentioned that this is used for static data types, and there's a sense of immutability in this. Is there a particular reason why it's immutable, or is there methods or some other system that you can use to have non-immutable types or non-immutable data structures in this?
Well, I will say this is just a use case, right? Or this is this is a tool specifically designed for static, immutable data. Okay, the short answer is if you want to use a non-immutable fields or something, that you might need to seek other tools. So yeah, it's just a different needs. Yeah, so personally, I don't see any reason we want to add mutable TableGen, make the whole concept TableGen mutable. Yes.
Okay, so primarily just because of the use case for this pattern, that's the proper way of handling it.
Correct.
All right. And if there's any other questions, it looks like we don't currently have any other questions. So I think for now, thank you for your presentation. And
okay.
I think we'll wrap up here.
Yeah, thank you.